Let's discuss example 2 of chapter number 9. We have an ideal transformer connected to a 220 volt RMS source, 60 Hz frequency. We have 100 turns on the coil on the primary side and 3000 turns on the secondary side. We have a load connected here. Secondary current is 2 ampere and the power factor is 80% lagging. So we know that if it is 80% lagging, that means the load is an inductive load. We are required to calculate primary current I1, secondary current I2, impedance of the load Z, individual components of the load, that is R and L since the load is inductive, and the peak flux linked by the secondary winding. It's going to be the same as peak flux linked by the primary winding, because again we are assuming it's an ideal transformer. So let's go ahead and solve it. Let's create another file. This was example number 1. Let me just copy this, copy, and let's create a new script, and this is example number 2. I'll save it in my lecture folder, chapter 9, example 2. Okay, I'm gonna go ahead and define all my variables. So my ES is 220, my F is 60, my N1 is 100, N2 is 3000, and my I2 is 2, and the power factor, load power factor is 0.8. Okay, now we know that N1 is 100 and N2 is 3000. That means it's a step up transformer. That means the voltage on the secondary side will be higher than the voltage on the primary side, and the current on the secondary side will be lower than the current on the primary side. So first calculate the primary current I1, and we know that I1 over I2 is N2 over N1, so that's going to be N2 times I2 divided by N1. Secondary voltage. Alright, so for secondary voltage we know that you have 220 volt across the primary side, and then we know N1 and N2, so we can easily find the secondary voltage. E2, remember E1 over E2 is N1 over N2, or E2 over E1 is N2 over N1, so that's going to be N2 times E1 divided by N1. N2 E1, N2 times E1 divided by N1. Load impedance. Alright, we know that the load impedance is going to be, the magnitude of the load impedance is going to be the magnitude of E2 divided by I2, and the phase of the load impedance, of course we know the power factor, so the phase of the load impedance will be cosine inverse of 0.8. So we can write down the load impedance. Let's say Z load equals magnitude, which is E2 divided by I2. I always do this, E2 divided by I2, and let's go ahead and put it in the rectangular form, since we will need the rectangular form in the next problem. Alright, so rectangular form is going to be magnitude times cosine of the phase, cosine D, or cosine, let's say cosine of we have 0.8, so cosine inverse, or actually just 0.8, because cosine of the angle is 0.8, so 0.8 plus I times sine of the angle of impedance. So sine of cosine inverse, so a cosine of 0.8, so sine of the angle. So I have, let me see, I balance the brackets. Okay, so basically I'm converting the polar form of complex number into rectangular form, where E2 over I2 is the magnitude of load, and then E2 over I2 times cosine of the phase, cosine of the angle is the real part, and cosine of the angle is 0.8, of course, plus j E2 over I2 magnitude times sine of the angle is the imaginary part. So sine of the angle, since angle is, you know, cosine inverse of 0.8, so I'm calculating sine of the angle over here. So that's my impedance. And then the individual components of the load. So R is the real part of Z load, XL is the imaginary part of Z load, and then from XL we can calculate inductor. L is equal to XL divided by omega, 2 times I times F. And finally peak flux linked by the secondary winding. Again we go back to the notes where we discussed the flux and induced voltage relationship, which is right over here. E induced RMS is equal to 4.44 F and peak flux. So let's go ahead and use this. And do peak flux equals, you're calculating secondary side, you can calculate primary side, it's going to be the same, but let's calculate from secondary side. E2 divided by 4.44 times F times N2. Okay, so that is it. Let's run this thing. And oops, alright, let's see, E1 undefined real. Alright, let's see, E1 is undefined since I defined ES. So let me go ahead and define E1 as well. E1 and ES are same. E1 equals ES. Alright, let's go ahead and run it again. Let's put a clear over here so it will clear CLC. So it's gonna clear this everything and then clear the screen as well. Okay. ES, okay, lowercase s. There you go, lowercase s. Alright, pi undefined should be lowercase pi. Alright, I made so many errors. F, uppercase F instead of uppercase F, I defined it lowercase f. Okay, alright, finally. So